Okay, so to find the shaded region of the first warm-up problem, you have to figure out the area of the two rectangles and the two triangles. So to do that, you take base times height on the rectangles. And we know that this dimension is 10 because the whole side is 28, and 28 minus 18 is 10. So then you multiply base times height, which is 10 times 3, and you get 30. And then you multiply the 30 by 2 to get 60 because there's two different rectangles. Then you have to find the area of the two triangles. And so because these two are because the two sides are congruent, you take 12 and divide it by 2, so you get 6 for this side and 6 for that side. And then you do 1/2 base times height, which would be 1/2 18 times 6. And when you do that, you cross that out, like that, and you get 54. Don't start. And you get 54. And then you multiply 54 by 2 to get 108, again because there's two triangles. Then you add the 108 to 60 and get 168 units squared. For the second one, to find the shaded region, you first have to find this dimension on the triangle. And we're going to find the area of the triangle and then subtract it from the total area of the figure. So this dimension is going to be 6, again because these two sides are the same, and you divide 12 by 2 and you get 6. And so then you do 1/2 base times height, again, and you have 1/2 6 times 6. You cross that out, and you get 3 times 6 is equal to 18. After that, you do 12 times 6 to get the area of the whole rectangle, and you get 72. Finally, you subtract 18 from 72 and get 54 for the area of the shaded region. Units squared. Lastly, we have the two circles. And to find that, you have to take the area of the big circle minus the area of the small circle. So the radius of the big circle A is 6. And the radius of the small circle B is 4. So you do pi times 4 squared, or you do pi times 6 squared minus pi times 4 squared, which is equal to 36 pi minus 16 pi. And you get 20 pi. And then you multiply 20 times pi, or 3.14, and you get 62.8. You get 62.83 units squared. I'm just going to keep going.
Okay, so we're going to take this a step further to find the probability of finding the area of one circle over a larger one. And so we drew basically a dartboard target defined with 4 different colors. We did black, orange, red, and green circles. We labeled them A, B, C, and D. So we wanted to find the probability of picking a point on the orange circle, the red circle, and the green circle out of the entire circle A. And so we did this by finding the area of circle B while the C and D included, and we subtracted it from circle A. And I have the work already done. So first off, we found the area of circle D by doing pi pi r squared, which would be pi times 4, which is 12.6 inches squared. And then we did the red circle, which would be 2 plus 2, 4, and this would be pi times 4 squared, which would be 50.3 inches squared. And to find the area of just the red ring, we would subtract for the red circle, we would subtract the green circle out of the red circle, and we got 37.7. We just continued this process for the rest of the circles, and we figured out that the area of just the red one would be 37.7. The green would be 12.6. The orange would be 62.8, and the black would be 141.4 inches squared. And then the total area of circle A, with everything included, was 254.5 inches squared. And so we did the part over whole for all of them. So the probability of picking a point for circle B would be 5%. Circle C, 15%. Circle B, 25%. And circle A, with the other circles subtracted out, would be 55%.
Theoretical probability is the likelihood of something happening based off of calculation, whereas experimental probability is the likelihood of something happening based off of testing. For example, the probability of flipping heads or tails on a coin is 50%. Theoretically speaking, though, if you flip a coin twice, you should get heads once and tails once. But if you do experimental probability, there's a chance that you can get heads twice or tails twice. Today we're going to show this by throwing a ball at a dartboard-like target. We're going to throw it 10 times to see if the experimental probability matches up evenly with the theoretical probability of what we should hit out of those 10 trials. So for the first time, we hit red. The second time, we hit black. And during the time while I'm throwing this, Trey is going to be keeping the tallies of how many times I've hit each color off to the side so we can run the numbers and show the actual probability. Experimental. Well, I missed. I don't think we need to show me actually hitting the thing. I'll just crop it out and we'll...
Okay, so after we tested the trials 10 different times, we figured out that we hit the green twice, red 4 times, orange twice, and black twice, which did not match up with the theoretical probability that we thought it would. We only hit the green 20% of the time instead of 5%. We hit the red 40% compared to the 15%. We hit the orange 20% compared to the 25%, which matched up the closest amount. And we hit the black 20% instead of 55% that we thought it would by our calculations of the area. And this was because it was just all random. We just threw the ball and this is where it hit. It doesn't have to be exactly by the calculation of the area. It's like hitting a bullseye on a dartboard. It is like 2% chance of hitting the bullseye, but people still hit it because of the aim. And that shows that experimental probability is not always the case of theoretical.
Wish you would.
Okay, so for our challenge problem, we are doing a time scenario for a bus station. So Nick arrives at a bus station. The buses leave every 17 minutes. He arrives at the station at 7:51 and has to be at work by 8. And the ride is 3 minutes long. What is the probability that he arrives on time? So I did this by setting up a number line. And so I have 7:51 and then 8 o'clock. And we know that he has to be on the bus by 7:57. So let's just mark that out right here. So he has a 6-minute window of free time. because of this, because they arrive every 17 minutes, any of this gray area he can be fine with. And so the probability of hitting that minute is 6/17, which is 35%. There's a 35% chance that Nick will arrive on time to his work.